Now we're going to take a look at something called an improper integral. In order to motivate the conversation, we're going to look at integrals similar to this one. Here we examine the integral from 0 to c of the function 1 over e to the x dx. And the question we're asking is, what happens to the area under this curve as c goes to infinity? We can see that as c gets larger and larger, the area under the curve continues to grow, but it also grows in smaller and smaller amounts. And so our goal is to figure out whether or not that area is itself finite. We're also going to take a look at integrals like this one, the integral from c to 1 of 1 over the square root of x dx, noticing that this function becomes unbounded as c approaches 0. And again, we want to ask ourselves, is it possible that the area is still bounded even as the function grows? We're going to need a few definitions in order to frame this conversation. So we'll start off with the definition of an improper integral. First, we see that an integral that is of the form from a to infinity of f of x dx, or from negative infinity to a of f of x dx, or from negative infinity to infinity of f of x dx. That is our first type of an improper integral, and we will refer to those as type 1 integrals. We will also consider integrals of the form the integral from a to b of f of x dx when f is unbounded somewhere on the interval a to b. We'll see that if there is a point of discontinuity, we can still consider the definite integral, and we will refer to those as type 2 improper integrals. In order to try to evaluate integrals that are type 1, we're going to need a few additional definitions. So, if f is a continuous function on the interval from a to infinity, then we're going to define the integral from a to infinity of f of x dx as the limit as b goes to infinity of the definite integral from a to b of f of x dx. Similarly, if we have a continuous function on the interval negative infinity to a, then we'll define the integral from negative infinity to a of f of x dx as the limit as b goes to negative infinity of the integral from b to a of f of x dx. Our last case is when we have a function that's continuous on all real numbers from negative infinity to infinity. In that case, we will define the integral from negative infinity to infinity of f of x dx in terms of the sum of two limits, the limit as b goes to negative infinity of the integral from b to a of f of x dx, plus the limit as b goes to positive infinity of the integral from a to b of f of x dx. We'll utilize some similar definitions for type 2 integrals. Here, if we have a function that is continuous on the interval a to b, but not including b, because the function becomes unbounded at b, the limit as x approaches b from the left is equal to either positive or negative infinity, then we're going to define the definite integral from a to b of f of x dx to be the same as the limit as c approaches b from the left of the integral from a to c of f of x dx. When instead our function is unbounded on the left-hand side of its interval, so it's continuous on the interval b to a, but the limit as x approaches b from the right of f of x is positive or negative infinity, then we will define the definite integral from b to a of f of x dx as the limit as c approaches b from the right of the integral from c to a of f of x dx. And finally, if f of x is continuous on the interval a to b, except at some interior point p between a and b, then we'll define the definite integral from a to b of f of x dx as the limit as c approaches p from the left of the definite integral from a to c of f of x dx, plus the limit as d approaches p from the right of the integral from d to b of f of x dx. With these 6 different definitions in terms of limits, we have 2 final definitions before we look at some examples. If the limit exists, then we're going to say that the improper integral converges. But if the limit fails to exist or is infinite, either positive or negative infinity, then we're going to say that the improper integral diverges. For our first example, we will return to the problem that motivated our original discussion. We're going to examine the integral from 0 to infinity of 1 over e to the x dx. And if you recall from that earlier animation, we saw that as x moves along the x-axis and we contemplate the area under the curve, we see that the area continues to grow, but the amount by which it grows gets very, very, very small. So we want to see if there is in fact a finite bound on that area. So we're going to use our definitions to say that this is the same as the limit as b approaches infinity of the integral from 0 to b of 1 over e to the x dx, which, if we want to rewrite that, we can write it as the integral from 0 to b of e to the negative x dx. And we know that the antiderivative of that is going to be negative 1 over e to the x evaluated from 0 to b. So when we plug in b, remembering that we're still taking the limit as b goes to infinity for each of these, we're going to get negative 1 over e to the b plus, because of the two negatives that we would get, 1 over e to the 0, which is just 1. And we can rewrite that as 1 minus 1 over e to the b. Well, as b goes to infinity, 1 doesn't change, but e to the b becomes unbounded, which means that 1 over e to the b goes to 0. So this, when we evaluate that limit, we get that that area is 1. So what originally appeared to be infinite is actually identically equal to 1. And so we see that this improper integral converges. For our next example of a type 1 improper integral, we're actually going to look at a family of improper integrals. We're going to look at the integral from 1 to infinity of 1 over x to the p dx. And we're going to see that for different values of p, we're going to get slightly different behavior. So we're going to have to consider a couple of cases. The first case we'll consider is when p is not equal to 1. We're also going to assume that p is not 0 for all of these cases, because that's an uninteresting case of the function. So when p is not equal to 1, then we know again that this integral is going to be the limit as b approaches infinity of the integral from 1 to b of 1 over x to the p dx. And since p is not 1, this becomes the same thing as the limit as b approaches infinity of the integral from 1 to b of x to the negative p dx, which is the limit as b goes to infinity of x to the negative p plus 1 all over negative p plus 1 evaluated from 1 to b. When we plug those limits of integration in, we get the limit as b goes to infinity of b to the, I'm going to rewrite that as 1 minus p over 1 minus p minus 1 to the 1 minus p over 1 minus p. We still haven't taken our limit. I'm going to tidy this up a little bit algebraically by factoring out a 1 over 1 minus p. And that's going to leave me with b to the 1 minus p minus 1. Okay, now we're going to notice a couple of things. We're going to again look at two different cases. So our first case is going to be that p is less than 1. If p is less than 1, then we know that 1 minus p, so 1 minus a number smaller than 1, that is going to be positive. That is going to be a positive number because we're subtracting something smaller than 1 from it. That includes the negative case. If we do 1 minus something like negative 2, we get a positive number. In that case, b to the 1 minus p as b goes to infinity. We have a positive number raised to a positive exponent going to infinity. That is also going to go to infinity. So that means that this limit is going to be infinite in the case where p is less than 1. And so that tells us that the integral from 1 to infinity of 1 over x to the p dx diverges in the case where our p-value is smaller than 1. We're still in the case where p is not equal to 1, but we have a second case we could consider, case 2, where p is bigger than 1. In that case, 1 minus p is a negative number. And when that happens, b raised to a negative power, as b gets larger, is going to get smaller and smaller and smaller and is going to go to 0. So we're going to see here that then we have the limit as b goes to infinity of 1 over 1 minus p times b to the 1 minus p minus 1 is going to equal negative 1 over 1 minus p, which we can rewrite as 1 over p minus 1, which will be a positive number. It's an area, so it better be a positive number. It's an area of a function sitting entirely above the x-axis, so it better be a positive number. We get 1 over p minus 1, and that converges. Now, if we go back to our original question, we want to now look at the limit as b goes to infinity of the integral from 0 to b, from 1 to b of 1 over x to the p, where p equals 1. So that is the limit as b goes to infinity of the integral from 1 to b of dx over x, which we know is the antiderivative of that is the natural log of the absolute value of x evaluated from 1 to b. So here we're going to get the limit as b goes to infinity of the natural log of b. B is positive because we're to the right of 1 here, minus the natural log of 1, which is of course 0. So we see that this is the limit as b goes to infinity of the natural log of b. But if b is getting larger, its natural log is as well. So this is also unbounded, infinite. So we see also that this integral diverges. So we have 3 cases. We'll wrap them up all here. So we have the case where p is less than 1. When p is less than 1, then we see that the integral from 1 to infinity of 1 over x to the p dx diverges. When p is equal to 1, because this becomes a natural log, this also diverges. But if p is bigger than 1, then the integral from 1 to infinity of 1 over x to the p dx converges, and in fact is exactly equal to 1 over p minus 1. For our first example of a type 2 improper integral, we will again return to our initial discussion and examine the integral from 0 to 1 of 1 over the square root of x dx. We saw that this was unbounded at 0, that the integral and its area, or the function and its area, grow as we approach 0. But we're again going to look to use these techniques to see if we can find a bound for that area. So we're going to rewrite this as the limit as c approaches 0. We're going to approach 0 from the right, since that's on our interval of the definite integral from c to 1 of, I'm going to write this as x to the negative 1/2 dx. And we know that that has a nice antiderivative, so we're going to get the limit as c approaches 0 from the right of 2 times x to the 1/2 evaluated from c to 1. So plugging in, we get the limit as c approaches 0 from the right of 2 times 1 to the 1/2, which is 2, minus 2 times c to the 1/2, which is, of course, just c, the square root of c. And we know that the square root of c is, or the square root of x is a continuous function at c equals 0, which means that we're allowed to evaluate this limit by merely plugging in 0. And so this gives us that this is the, we no longer need the limit when we do that, and we just get 2 minus 0, which is 2. So we see that the integral from 0 to 1 of 1 over the square root of x dx converges, and we define that area under that curve to be precisely equal to 2. For our next example of a type 2 improper integral, we're going to examine the integral from 0 to 2 of 1 over x minus 1 squared dx, and we'll notice that this is unbounded at x equals 1. So we know our rule tells us we're going to split this into two integrals. The integral from 0 to 1 of 1 over x minus 1 squared dx plus the integral from 1 to 2 of 1 over x minus 1 squared dx. And we're going to examine each of those using a limit. So we'll just work with this one on the left first. So we're going to examine the integral from 0 to 1 of 1 over x minus 1 squared dx. And our rule tells us, since 1 is the place where this is unbounded, this is going to be the limit as b approaches 1 from the left, the integral from 0 to b of 1 over x minus 1 squared dx. And a fairly straightforward substitution and anti-differentiation gives us that that is the limit as b approaches 1 from the left of negative 1 over x minus 1 to the first, evaluated from 0 to b. So when we plug in b, we get the limit as b approaches 1 from the left of negative 1 over b minus 1 minus negative 1 over plugging in 0, negative 1. And we can see as b approaches 1 from either direction, this denominator is going to 0, which means this entire expression is unbounded, is going towards infinity, which means that this limit itself must be infinite, which means that our definite integral diverges. There is no finite bound on one of those two integrals, which must mean that the entire thing diverges. It's not possible for half of it to diverge while the other half could potentially not diverge, but it doesn't matter because we're looking at the entirety of the area from 0 to 2, and so this entire thing diverges. We've seen before that there are some definite integrals for which we cannot actually compute antiderivatives analytically, but we might still want to figure out whether or not those integrals converge if we're looking at them over infinite intervals or if we're looking at them over regions in which they become unbounded. So in order to do that, and in order to give us a starting place for more complicated antiderivatives, we can use something called the comparison test. So if we have a known integral that either converges or diverges, we can then choose to compare an unknown one to it. So if we have two functions, f and g, and they're both continuous on the interval from a to infinity, and we know that f of x is bigger than or equal to g of x, which is bigger than or equal to 0. So we're only looking at positive functions here. And f is bigger than g for all x greater than or equal to a. So if you were to look at the graphs of the two of them, f of x would be above g of x from x on towards infinity. Then we know that if the integral from a to infinity of f of x dx converges, so does the integral from a to infinity of g of x. Hopefully that makes some intuitive sense to you because g of x is smaller than f of x on the entire interval, so its area must somehow be smaller than the finite area we've determined for a. Conversely, if we know that g of x, or the integral from a to infinity of g of x dx diverges, in other words, we've determined that the area under g of x is not bounded, then it follows that the integral from a to infinity of f of x dx, the larger function, must also diverge. Its area must also be unbounded. We'll look at a couple of examples to see how this might work in practice. To try out these comparison tests, let's consider the function or the integral from 0 to infinity of e to the negative x squared dx. We've looked at this previously in the video about numerical integration. This is one of the functions that does not have an antiderivative that we can come up with analytically. And so, in order to determine whether or not its integral between 0 and infinity exists, we can try a comparison test. So what we're going to do is we're going to notice that for x greater than 0, e to the negative x squared, which is the same as 1 over e to the x squared, must be less than or equal to 1 over e to the x, because we're using the facts here that x squared is bigger than x for positive values of x. And so the denominator is bigger, which makes the entire expression, 1 over e to the x squared, smaller than 1 over e to the x. We know already, because we did it earlier, that the integral from 0 to infinity of 1 over e to the x dx diverges, or converges. This one converges. And so that tells us that the integral from 0 to infinity of 1 over e to the x squared, which is the one we started with, also must converge. Now notice we have not found a specific value for it, but we do know that it converges and that it is going to be less than our original value. For our next example of a comparison test, we're going to consider the definite integral from 0 to 1 of sine x plus 1 over x to the 5th dx. Now, we have not done yet an integral with which we can compare this easily, because we only considered 1 over x to the p on the interval from 1 to infinity. So let's look at 1 over x to the 5th on the interval from 0 to 1. So we're going to consider this integral from 0 to 1 of 1 over x to the 5th dx first. Well, we know that that is, because that is unbounded at 0, that is the same as the limit as c approaches 0 from the right of the integral from c to 1 of 1 over x to the 5th dx. And so if we take an antiderivative of that, that is x to the negative 5th, so we're going to get negative 1/4 x to the negative 4th from c to 1. Plugging in, we get the limit as c goes to 0 of negative 1/4 plus 1 over 4c to the fourth. And now we know that as c goes to 0, 1 over c to the fourth, since the denominator is going to 0, that whole term is going to infinity, which tells us that the integral from 0 to 1 of 1 over x to the fifth dx diverges. Let's see how that's helpful to us. We know that sine x is always between, or on the interval from 0 to 1, sine x plus 1 is always greater than or equal to 1. Since 1 is smaller than pi over 2, sine x is residing, or thinking about it in terms of the unit circle, it's in the first quadrant where sine is positive. So sine x plus 1 is bigger than or equal to 1, which then tells us that sine x plus 1 divided by x to the fifth, because again, we're dealing with all positive numbers here, that must be greater than or equal to 1 over x to the fifth. And therefore, since the integral from 0 to 1 of 1 over x to the fifth dx diverges, the comparison test rules tell us that the integral from 0 to 1 of sine x plus 1 over x to the fifth, if you were to graph that function, it would sit above 1 over x to the fifth on the interval from 0 to 1. So that tells us that this must also diverge. We'll finish with a recap of some of the main ideas we saw. First, we have the definitions of our improper integrals over infinite intervals. And there are 3 ways we can think about those. Then we have the definitions of our type 2 improper integrals, where the function becomes unbounded at some point on the interval, once again defining each of those in terms of a limit over that interval. And we finish with a reminder of what it means for an improper integral to converge versus diverge, as well as a reminder of our 2 comparison tests for integrals that we may not be able to find antiderivatives for easily.